Welcome.
Okay. So sorry for this problem of compatibility with my Macintosh. I don't know why is happened. So my name is Daniele Forni, and I'm here to present our paper entitled High and Very High Strength Steels Under Harsh Conditions of Temperature and Loadings. In the last year, we can remember different events of this type. For example, the 9/11 terrorist attacks, the Deepwater Horizon disaster, the BASF headquarter disaster, the Rigopiano snow landslide, the highway bridge explosion near Bologna, as well as the Morandi Bridge collapse. The question is, what are the common things among these events? They are all dynamic events characterized by combined effect of actions. They lead, in fact, to a large number of fatalities and high cost for reconstruction and demolition. So the main objective of our project was to understand the mechanical behavior of both structural and reinforcing steels under the combined effect of dynamic loads and temperatures. Today, we will focus the attention on the structural steels named as 690 and 960. And you can see, for example, a simulation of a steel column which I've done. We obtained the samples for the mechanical characterization, as you can see on the top right of the images, starting from the raw section of the material. But we know that the thickness, the material is not homogeneous within the thickness of the material, because we have a peripheral region which has a martensitic microstructure, while the core has a binitic one. For this reason, we obtain two types of samples made of different submaterials from the core and the peripheral zone. And this is the experimental plan we did. So starting from the quasi-static conditions to the high strain rate test at room temperature, then by keeping the same loading condition, we did also the high strain rate test at high temperatures. The dynamic characterization has been performed by using a modified Hopkinson tensile bar in the plus the addition of an induction water-cooled heating system, as you can see on the image. The tests were performed firstly by heating the sample at the desired temperature, and then by keeping the temperature constant for some second or minutes, and then performing the dynamic test. Only at room temperature, due to the shape of the coil, we recorded the failure process by means of an high-speed camera to record the failure process of each sample. In this slide, I have reported some of the different mechanical properties that we can record for each test. For example, the proportional limits at 2%, the strength corresponding to different levels of strains, the ultimate tensile strength, as well the modulus of resilience and toughness. So let me say something about the room temperature test very quickly on this stress strain graph, in which, for the sake of simplicity, we have reported only the peripheral zone for the two materials, so S690 and 960, we can see the strain rate sensitivity starting from the quasi-static test to the high strain rate test. The strain rate sensitivity is also well represented in these plots, where the dynamic increase factor, as the ratio between the quasi-static to the dynamic mechanical properties, is depicted. On the left, this ratio is reported for the yield, while on the right is depicted for the ultimate tensile strength. highlighting the different strain rate sensitivity of core and peripheral zones. So something about the temperature effect. It's obvious, we know, that at increasing temperature, we have a decrease in the mechanical strength. But we have observed in particular that up to 400, 550, so the yellow and the orange curves, we have only a limited decrease in strength. While for higher temperature, let me say starting from 700 Celsius, the decrease is more evident, while and also the total elongation, as you can see on the red curves. This is also well represented in these two 3D surface plots, where both yield on the left and the ultimate tensile strength on the right have been can be represented. So to say something about the material models, we can say that, and we know that there is an increasing demand for complex numerical simulations of civil engineering structures. This is to evaluate the structural robustness under extreme loading conditions, for example, of high temperature and dynamic loads. The link between the mechanical properties and a numerical simulation is a material constitutive law. So we have considered three different approaches. The first one is by calibrating the experimental test results with the elastic elliptic perfectly plastic model proposed by the Eurocode 3, but under dynamic conditions. And the last two are the commonly constitutive relationship describing the mechanical properties of metallic materials at high strain rates. We know the names are the Cooper-Simon and the Johnson-Cook relationships. The choice amongst these three approaches can depend on different aspects. For example, the problem to be simulated, or in the case of the last two, because I'm talking about Cooper-Simon and Johnson-Cook constitutive material model, because they are the most commonly implemented and easy to use constitutive relationship in the finite element programs. So in the first case, so for the elastic elliptic perfectly plastic approach of Eurocode 3, we have reported an example of the 690 at 250 strain per second, and we can see that the model we have calibrated can safely predict the real mechanical behavior of the material in the range of the strain and the stress reported on the code. So something about the other two models, because the Johnson-Cook models, by means of the 5 constitutive parameters, is able to predict the true stress versus true strain in a wide range of strain rate and temperature. As you can see on the right plots, this model is able to fit very well the experimental data. On the other hand, with the more simple Cooper-Simon constitutive model, is it possible to, by calibrating only 2 parameters, to predict the yield tensile strength at increasing temperature, but in its original formulation only at room temperature. So to conclude, we have investigated 690 and 960 structural steel as a part of this investigation campaign to reveal more information and facilitate their widespread use. Following a multi-hazard approach for the civil engineers, we have highlighted the necessity of understanding the mechanical properties of materials under coupled effect of extreme actions. From the experimental test, we can say that the materials are strain rate sensitivity both at room temperature, and the main properties at high temperature have been highlighted. And lastly, we can see that the three approaches of the models were able to fit the experimental data, we can say, very well. As a feature development in the last seconds, we would like to study also the green area in which the strain rate is in the medium range. So for example, for earthquakes, but also at different temperatures. We can go to study also other structural stils, for example, 235 and 460 stils. And of course, one of the more important feature development can be to study the effect of ductile to brittle transition, for example, by testing at temperature below 0 Celsius, of course, under dynamic conditions. And this is all for me. Thank you for your attention, and excuse me again for the beginning of the presentation with the error of the sharing.